So you're going to say that you're going to have shear stress at point A, and shear stress at point A is a white flange, like what we have before. So we call it a white flange analysis. And what we have is just a single Q. Now, which area do we take, right? So again, rule number 2 or 3, I cannot remember now. Okay, the analysis starts from where? Y max, yes or no? And then it pulls down here. So this is our analysis direction, right? So the area that we are going to consider is just this area over here, right? Makes sense, yes? Okay, so from here, the Q for point A. Now for this case, you don't need to do left and right, yes or no, right? The end point is from here, it goes to one end point. You need to consider that arrow, that area, okay? You don't need to look at end point number 2. You don't need to do that, right? So for this case, shear at point A, the width is equal to 0.7. So I like to do width, depth, y bar. So the width is 0.7. The depth is 0.2. The y bar is again 3 divided by 2 minus by 0.2 divided by 2, right? So this is equal to 0.7 times by 0.2 times by 1.5 minus by 0.1 is equal to 0.196, right? So this is equal to 0.196 inches cubed. So we can directly find the shear stress at point A. So shear stress at point A is equal to Vy over Izz, right? Multiplied by 0.196, divide by the thickness, which is 0.2. And then down here, you don't need to consider 2. Down here is 1, yes or no? Why 1? Because it's Q, and why Q? Because it's a white what? White flange. Okay. So this will be equal to 0.196 divided by 0.2 divided by, so it's 0.96. It's exactly the same. 0.196. Is it 0.196? 0.196 divided by 2 is equal to 0.98. Right, Vy over Izz. So what we realize from this analysis is stress at point A, the shear stress at point A, and the shear stress at point B, they are the what? They're the same, yes or no? You can see that, yes or no? Right, the shear stress at point A and the shear stress at point B are exactly the same. Okay, so now we want to look at the stresses, okay, the maximum stress where Q is maximum. Okay, so we want to find the position of Q max, and for this case we know it is at the what? Okay, it's at the centroid. For this case, okay, for this, not every case is at the centroid. For this case, is at the centroid. I repeat again, for this case, it's at the centroid. So I'm going to copy and paste. Right. So we are going to find point C. So this is where our centroid is. Right. So my suspicion, or our suspicion, a very intelligent guess, is at point C is where maximum shearing stress will occur. Now, so what we're going to do is we're going to find the shear. So I'm going to call this top. And I'm going to call this bottom. Okay, one is top, the other one is bottom. I'm going to construct the Q. Okay. So down here is the longest. So this is our Q, right? So this is our Q. Our Q are flowing. So I want to, I want to show you. This is just to show you. I want you to have the confidence. Okay. So we are going to find the shear stress at point C from the top by analyzing the top. Okay, I'm going to analyze the top section, or we are going to analyze the top section, right? So you know that the top section is a box beam, whereas box beam is going to be 2Q. So the area that we are going to analyze, that we have to consider, is this area now, this whole area. Okay, because it starts over there, the start is a common point, is this whole area, right? So when that's the case, the Q at point C is equal to Q of the flange plus by the Q 2Q of the web, right? We have web on the left hand side, web on the right hand side. So the width is 1.4, the depth is 0.2, so this is equal to 3 divided by 2 minus by 0.2 divided by 2 plus, so the web is left and right, so 2, the height, the width is 0.3, the height is 1.5, and then the y bar is 1.5 divided by 2, right? So how I divide this is I divide this way, right? This is how I divide it. So from here, this will be equal to 1.4 times by 0.2 times by 1.5 minus by 0.1. So it's equal to 0.392, right? So we get 0.392 plus by 2 times 0.3 times 1.5 times 1.5 divided by 2, 0.675. So this will be equal to 0.392 plus by 675 is equal to 1.067. Okay, so 1.067 inches to power 3. So from here, the shear at point C. Now, by looking at this, right, the first moment of area at point C, right, is much larger. Point A is only 0.196. Point B is only what? Point B is only 0.392. Right. This one is the maximum is 1.067. Right. So we know that this will be also be equal to what? Our town what? Max. So we have Vy over Izz multiplied by 1.067 and then divide by the thickness will be 0.3 and then you have to multiply by 2 because it's what? Box beam. Okay, so from here this will be equal to 1.067 divided by 0.3 divided by 2 is 1.1778 1.7 okay 1.7783 Vy over IZZ, or in terms of fraction is 1067 divided by 600 Vy over IZZ. So you know that tau max is equal to 10 times 10 to the power 3. So this will be equal to 1067 over 600. So it's your Vy over IZZ. So your Vy over IZZ will be equal to 10 power 3 times 600 divided by 1067. So this is equal to 5.6. I get 5.623 times 10 to the power 3, right? Times 10 to the power 3, and these are in pounds over inch to the power of 4. Okay, that is our ratio. Now, what if you decide to take from the bottom? Okay, what if you decide to take from the bottom? So I'm going to copy this again so you can see the figure better. So we're going to take this from the bottom now. Right. So we're going to analyze by find stress C, and we're going to analyze from the bottom. Right, we're going to analyze from the bottom. So from the bottom, right, if you look at the bottom, is a what? White flange. And it's a white flange, you only have what? Q. So the bottom is white flange, so you only need to consider this area down here. Okay, you don't need to consider the left hand side, right? Because it has two different endpoints. You have one end down here, and you have a different endpoint over here. It don't come together. Okay, so from here, right? From here, we will have what? We will have a analyze from the bottom white flange. So we have Q at point C will be equal to the Q of the flange plus by Q of the web. So the flange is equal to 0.7, the width is 0.7, the thickness is 0.2. So this is equal to 3 divided by 2 minus by 0.2 divided by 2. That's your y bar, plus the width is 0.3, the depth is 1.5. Then you have 1.5 divided by 2. Okay, so this will be equal to 1.5 minus by 0.1 times 0.2 times 0.7 is equal to 0.196 plus by 0.3 times 1.5 times 1.5 divided by 2, 0.3375. So this will be equal to 0.196 plus 0.3375, 0.5335, right, inch to power of 3. So now I'm going to do right over here. So we know that the shear max or the shear at point C, down here we don't know whether it's shear max, right? It's 0.5335, right? We don't know, right? The other one is obvious because it's 1.067. This one we don't know. So we just call it the shear at point C if we're not sure. So this is equal to Vy over IZZ, 0.5335, right, divide by the thickness, which is 0.3. So this is equal to 0.5335 by 0.3. So what we know is this value is 1 down here because it's what? White flange, okay? I know you don't need to put down, but I just remind you. Right? So the shear